Okay, good morning everyone. So we're back to the class. So today we will start to introduce for the materials. So we will introduce some like the key material for the semiconductor device. And also we'll start to go through the basics related to the why the crystal structure for the semiconductor device can give us some like the very unique properties. By the way, I think there's some problem for this microphone, so it might not, like if you sit in a little bit far from me, probably you won't hear the voice clearly. So if you would like to switch the seat, you can feel free. But I'm not sure that whether I can fix this. Okay. So first one is that we have to understand how to form the semiconductor device. So there will be the several different device architecture in all of the device that you will use in the future. They can be classified as three different basic architectures. So if you consider for how to form the semiconductor device, first we have to understand from the first stage, which will be the materials. And so that means that, for example, in the last class, in the introduction part, we have explained that in the future we will talk about the PN junction and PN diode. So in terms of PN junction and PN diode, I think the materials here indicate as for example, we have the two different materials. Which one will be the P type and another one will be the N type here. So these are the two most important I would say like the doping in the case of all around of the semiconductor device. And in this case we can dope the P type or N type and change the materials property. So the N means that this is materials that are full of the electrons, and P means that this is the materials that are full of the holes. So that's the first part. When we start to design our device, it's always starting from the materials. And the second part, which is the junction. So the junction means that we start to put the N and P together. So if we start to put the N and P together, and we can foresee that they can be some of the different things can be happen in the place between the P and N. So this is a place what we call the junction. And the junction is a place that has a lot of the physics and sometimes also involved for the chemistry can be happen, because right now we try to put the two different materials connect to each other. So you can foresee that once it being connected, the connect interface, it must has something change, and in the end this change will lead to the different mechanism in overall of the systems here. So in the second part we will start to discuss that what happened will in the inside the junction. And the last one, for sure, we start to move to the device. So the device in here, if we look at the simple PN diode, that's already considered the overall it's a device. So in here, the overall consideration for P and N, that's a device. Of course, that's a very simple one. So we use a PN as a very basic for the explanation purpose. But the one we are interested in is definitely not only for the PN. The one we are interested in is a real transistor. For example, we are interested in the MOSFET. So as I already illustrate in the last class, that the MOSFET is a structure whether we have the P-type substrate and we have the N plus in the drain side and source side. And also, we have the dielectric. We have a dielectric here. And the one we use most often is the silicon dioxide. And then we have the gate. If we look at this is a structure for the MOSFET. So if we look at a little bit details for the structure of the MOSFET, you can also find out that actually the PN junction is already existed in the MOSFET structure, which is here. So in this place, you have the interface between the N and P region. So therefore, there is a PN junction in this region. And also, on the right hand side, there is another PN junction here. So this actually suggests that even for a transistor like the MOSFET, actually the PN junction plays a crucial role for the device characteristic, because in here you only consider one PN junction, but in the transistor like the MOSFET, you actually have to consider the two PN junction. And also the bias here at the drain side is not a constant, is will be very depends on your operation condition. So understanding the PN junction is very crucial, because in the end we will certainly use PN junction to understand the MOSFET as well. So that's the basic. That's the basics. The structure, that how to form a device. We will start to talk about from the materials, and later on we put the two materials, and then that will become the junction. After we understand the junction, we'll move on to the device, and the course will be also organized in this way. So that means in the later part, we will start to introduce the materials. So first, let's look from the very fundamental, from the the periodic table that what actually the chemistry species that we can use for as a semiconductor materials here. The first one, we will look for the group 4. In here, we have several important elemental semiconductor, which are the carbon, silicon, and germanium. And these are, generally we call this as a elemental semiconductor. So the elemental, it means that this semiconductor can be formed by only one kind of the chemistry species as shown here, which can be carbon, silicon, and germanium. And this is found in the group 4 of the periodic table. And that's composed of a single species of the atom. And among three, the most important tools are the silicon and germanium. These are very important elementals, the material that we can use for the semiconductor device. And also, on the other hand, we can consider to use two different piece of the atom, and we combine together and become the semiconductor. For example, if we try to put the group 3 and group 5, these two atoms together, then we can make generally what we call the compound semiconductor. So for example, as shown here, the gallium arsenide or the indium phosphide, which are the very important compound semiconductor materials here, which is a combination between the gallium arsenide or indium phosphide. So that's the case. We call this as the compound semiconductor. So the compound semiconductor are formed from the spatial combination of the group 3 or sometimes with the group 5 elements. So that's a combination with the group 3 and group 5 elements. And these two elements, or sometimes we call as a binary compound. For example, such as gallium arsenide, gallium phosphide, that can be formed by the one in the group 3 and the one in the group 5. And also, beyond the two elements, it is also possible to have the 3-element combination. For example, here, aluminum gallium arsenide. That's also very popular semiconductor materials that we are using now. Or aluminum gallium nitride. That's also the one that's very popular for the materials that already exist in our daily life. So these are the 3-element compound material. And usually the X here, as I mentioned, the X is indicated as a fraction of the lower atomic number of element component. So it means in reality, we are not only just simply call this as aluminum gallium arsenide. It could be also sometimes has a percentage here. For example, we have 0.2. That means 20% of aluminum. Here is 0.8. Or that can be also often seen in the aluminum gallium nitride here. So that means this is the different fraction of the aluminum and gallium arsenide, gallium. So here is an overview of the semiconductor materials here. If we consider for the elemental semiconductor, and the germanium and silicon are the two most important ones that we have been used for the decades here. And germanium is the first material it's the first materials that's used in the integrated circuit. And this is a trace material. The germanium has some of the material property. For example, it has a small band gap. Later on, we will explain what does the band gap mean here. But here, just a quick overview that what's generally like a material property for germanium. And first of all, it has a small band gap. And second, it has a poor thermal stability. And the last one, the gallium arsenide is soluble in the water. So that means that the gallium arsenide is not a very stable material here. If we look at for the success of the MOSFET, one of the key important feature for the MOSFET is that we need to have very stable silicon dielectric, and which means that silicon dioxide is a very stable material. But unfortunately, the gallium arsenide is not very stable. And consider that's why later on the silicon, when people develop the silicon, when people found the silicon, and then later on silicon becomes dominated in the semiconductor industry. So this is because for the following few reasons. The first one, the silicon is one of the most common elements. And also, the band gap is larger than the germanium. So silicon band gap is 1.1 electron volt. This is something that the number that you should be aware of, because this is become the reference later, like when you justify the other material, whether it has a large or smaller band gap, it's always to be referred to the silicon case. So if we have the band gap larger than silicon, that's what we call the wide band gap. If we have a band gap smaller than silicon, we call this is smaller band gap material. So the number for the silicon band gap, that's very important. And then the next one is silicon dioxide is very stable. So that's why later when we start to use silicon as a semiconductor material, and we found out that it's actually a really good candidate because of the silicon has a large band gap, and also silicon dioxide is a very stable materials, and also silicon is one of the common elements in the world here. So if you look at for the advanced FinFET, this is TSMC 16 nanometer FinFET technology here, and they still use silicon dioxide, and the silicon dioxide is in the here below the gate, below the gate region, still use SiO2. Of course, they can be the combination of the several advanced dielectric, but the silicon dioxide still be the one that pretty often used in the current technologies. And since we're starting from the materials here, and then later on, it's also important to understand that how actually the device evolution. And in here we have shown this is a FinFET structure, and then evolution trend is actually can be seen from here. We're starting from the planar MOSFET. This is a typical structure for the MOSFET here, and we start from the planar and start to move due to better control the electrostatic in the channel to try to reduce offset electric current. As we have said from last class, there are the two different approach. One is called using the SOI. That's a silicon on insulator. So therefore, this structure, what we call this is FDSOI. That's the full name is a fully depleted silicon on insulator. And another approach right now is pretty dominating for the advanced technology, which is a FinFET structure here. That's the something you can see from here. This is a real TN image of the FinFET, and this is a schematic for the FinFET structure here. And no matter for which kind of the structure here, the oxide is always very crucial in the case of the MOSFET technology, because we need to have the very stable dielectric that can allow us to have the better control our device, but also to have the low leakage current that can be good for the reliability issues. And here is another overview for the compound semiconductor that's related to the 3-5 materials here. So as I say, that there are several very common use for the compound material. The first one is gallium arsenide. So gallium arsenide is the materials has several unique material property, which is first one is a direct band gap. And the second one is a high electron mobility. So, because of this unique property, especially the high electron mobility, so gallium arsenide is very suitable for certain application, especially for the high-speed communication here. And in here, I just put one of the paper. That paper is published in the 1993 here. First, you have to know that the gallium arsenide is already the technology in our cell phone, in the many applications related to communication. So that means that this is real technology we are using now, not like the technology only happen in the paper or only happen in the academics. It's a real technology that people often use for the communication. And if you look at the history of the gallium arsenide, that's already developed in the 1993. And this paper is called gallium arsenide base heterojunction bipolar transistor for very high performance electronic circuit. This is a very great example that actually for semiconductor, I'm not saying for all of the field in all of the domain, but I believe that at least in the semiconductor domain here, whatever you look at for your research, whatever you are done on the research, actually in the end, it always has potential become the real product. That's the influence of life. And that means actually the semiconductor, this kind of the knowledge is very practical. This is not knowledge that only for the paper publishing, only discussed in the paper, in the journal or in the academic, because in the future all these will become the real technology people use in the life. So the gallium arsenide is one example that has been already developed in the 1993, but nowadays very often used daily life. And one more thing is interesting to know that if you look at the author of this paper, there's one name probably you have been heard of, but probably when you enroll in the NYCU, the professor, the Frank Chen, Zhang Maozong, who is not currently the president, but he was the president of the NYCU NCTU before. So you can look at that actually in the 1993, he already involved in the developing this very high-speed communication technology here. Okay, so that's one of the history, a very brief history for the gallium arsenide. Of course, for 3.5, there are some other candidates that are very promising. Another one is gallium nitride. So also, gallium nitride has several unique properties. The first one is still the same. The gallium nitride feature with direct band gap. And also, gallium nitride has a good property of the high electron mobility. So now you can see that if you compare with the gallium arsenide and gallium nitride, then you found out that it seems that all of the good advantage from the gallium arsenide, that also gallium nitride has this good property as well. And then the last one, which is the most unique one, that the only gallium nitride has, which is we have the large band gap here. Especially the large band gap here is the gallium nitride has a 3.4 electron volt. That's actually 3 times larger than the silicon. So in the last slide, we have mentioned the silicon number is a 1.1 electron volt, but for gallium nitride we have a 3.4. That means this is a pretty large band gap here. And also, another thing that for the good thing for the direct band gap is that it can be used for the LED technologies. So if you look at the nowadays for the LED technology, all of them is made by using the gallium nitride material, like the projector inside the projector, the lamp is made by the LED, and then if you have the very some of the very advanced the technology, they all use the LED as a lighting. So the gallium nitride is no doubt for sure that's already being used for our life for a very, very long time here. But the large band gap here, although it's just a material's property, but actually it still suggests something good electrical characteristic. So we will discuss this later. And also, if you look at for the group 4, as we previously said, that group 4 is a elemental semiconductor that's usually made by a single species of the atom, but it can be made by the combination of the two group 4 materials. For example, the silicon carbide is one of the example. Silicon carbide is also the materials that feature with a large band gap. And in addition to the large band gap, it also has a very good property of the thermal conductivity. So the thermal conductivity, that means that this kind of material is very good for the thermal dissipation. If you are, I think you must be heard about, like for example, for the server, you need to have the very special design of a cooling system, because the server running actually is generate lots of heat, and therefore you have to put the very good thermal dissipation system, like the water cooling, like the air cooling, to have the better dissipation. If you look at for your cell phone, that's the same. If you try to use your cell phone, play some like the video game, after a certain while, you definitely will find out that your cell phone becomes very hot, and that's because of during the computational time, actually it will start to generate lots of heat, and therefore we need to have the very good technology for to try to bring this thermal away, and that's how we call the thermal dissipation. And in addition to the additional thermal dissipation system, the materials itself can be also be one of the good system that can to have this thermal to reduce the thermal issues, because due to the if this material has this good thermal conductivity. So that means if we use silicon carbide as a material, and that can already bring the advantages that the thermal issues inside the component can be highly reduced compared to the silicon materials here. So therefore, if you look at for the gallium nitride, silicon carbide, this kind of wide band gap, this kind of compound semiconductor, they both have some good property of the, for example, large band gap. And also, if we use silicon carbide, that also have the some of the good property of the good thermal conductivity. And this actually suggests that these materials are very good for some of the application that would be used for the high temperature environments. So generally, that's we call this as a high temperature application. So then you have to understand that if we try to qualify our semiconductor product, our electronics, that can by consider the different application scenario, we have the different spec. In the general electronics that we use all over the day, that we sometimes just call this as a consumer electronics. And also, for the some of application, we also need to develop another set of the electronics. For example, we have the automotive electronics. So automotive, it means that this is electronics that mainly used for the vehicle. The vehicle, for example, the general, like the car or the electrical vehicle. And also we have the electronics that can be used for the space. So that's we have the space electronics. Of course, there's a general, there's a huge different spec for these electronics, because you can see that for the one we use consumer electronics, we usually expect the lifetime for the consumer electronics could be 3 to 5 years, because after 3 to 5 years, you already consider to replace your cell phone. You want to buy the new one. And also right now, nowadays, for the laptop, that's generally you can only use to, I think the 5 years is already very good. If you have the one laptop that can be used 5 years, that's already considered very good, like the robustness. But in the case of some of the low-end laptop, you probably can only be used for 1 and 2 years. So that's the status for the consumer electronics. But for the case for the automotive, that's a different scenario, because the automotive, if you drive a car, if you purchase one car, you expect you will like to use this car for the 10 years, sometimes for 20 years. If you check your parents, your grandparents, they might already have the car that have been used for the more than 30 years and 40 years. So that means for the automotive electronics, we have to use very high standard of reliability. And also the automotive, this car is run every day on the road, even in the during the night or in the very the hot condition during noon. And therefore this automotive electronic has to be pretty verified with the very extreme temperature. And also the additional extreme case that can be the space electronics, because when you try to launch the satellite in the space or exploration, actually the space environment is completely different from the environment on the Earth. And therefore, it also requires a semiconductor device that can be survive in the lowest environments here. So in general, if we consider the consumer electronics, the environment that we can use the consumer electronics is roughly below 125 Celsius degree. So you won't, at least on the Earth, you definitely won't actually put your cell phone in the environment beyond 100 Celsius degree. So that means that when they make these consumer electronics, they just have to make sure that the device can survive maybe up to 125 Celsius degree. But that's a different spec for the automotive. For automotive, then we have to put a very high standard of the reliability, and therefore these electronics need to be survived for more than 200, roughly around at least 200 Celsius degree. And then for the space, that's completely different scenario. I think all you know, the space has a very extreme temperature environment. Some planet has a temperature beyond the 300 Celsius degrees here. And therefore, the materials with a high temperature is the material that can have the good property for the high temperature environment, can be suitable for the application, for example, using the automotive or the space electronics. That's why the large band gap and good thermal conductivity, it has several like the very unique advantage that can be used in these domains. And here is one example. If you check the NASA's website, and then you will find out that there is a dedicated page is talking about what kind of the semiconductor they use, put in the space exploration, they put in their space satellite. And this, they very clearly mention that they actually use the silicon carbide material for all of the space technology inside the NASA's, the space spaceship, space exploration, and so on and so on. They all use this kind of the silicon carbide material, and this is because the silicon carbide has a good property in terms of the band gap and then the thermal conductivity. And if you try to look at, you just go to the IEEE and you look at for the journal paper like the IEEE electron device later, you will find out that actually NASA, they already published the several good results in the IEEE EDO, and the results are related to the silicon carbide circuits for the environment that has a higher temperature, more than 500 Celsius degree. And this is purely for the space application. So here just one idea that how this material property in the end will influence our, not only for the device structure, but also for the application. So the wide band gap material, that's one example that due to this unique property, therefore we can start to advance our technology in the completely different domains. And here is some more details related to the band gap. We will talk about the band gap later, that why we have to use this concept to illustrate the certain material property for the semiconductor. But in this slide, just quickly, like the summary, like what would be the band gap in the different semiconductor material. So as I already said, the silicon, which is the most important one, that the band gap is related to 1.1 electron volt. And when we try to calculate the band gap, actually we refer to the difference between the top, which is a conduction band, and then the bottom is a valence band. So the band gap is basically the difference between the top of conduction band and then the bottom of the valence band. We will also explain that what does the conduction band and valence band mean later. But here just have to know that there's a number called the band gap, and in the silicon case, it's a band gap is 1.1 electron volt, and in the case of a germanium, we have already summarized in the previous slides that germanium has a small band gap. So the real number for the germanium is a 0.667 electron volt here. And these small band gaps generally has an issue that has the higher leakage current, because the valence band, below valence band, is a place full of electrons. So we have electrons here below the valence band, and when during the certain operation or during the certain temperature environments, these electrons will start to gain some energy, and they will start trying to jump across the band gap region. That's usually we call the forbidden region. This is we generally call the forbidden region. So this electron will try to cross over this forbidden region and reach to the conduction band. If this behavior is successful, and that will become the current. So that's why we have the current flow in the semiconductor materials. If the electrons in the valence band can jump across and reach to the conduction band, and thus become the current. And therefore, this actually illustration in here is clearly shows that if we have this band gap is smaller, that means the distance is shorter, right? So the electron is easily jump across this region and reach to the conduction band. So we can have the very high leakage current in the case with the germanium. And if you look at for the extremely case like the diamond, we all know if you don't have any knowledge related to the semiconductor, you just have the high school physics and chemistry, we all know that diamond is a material that should not have any conducting property. Diamond should be the material that purely showing the insulating property. And that means they should have no current inside the diamond. Also, we can use this band diagram to understand why they should have no current in the diamond. Because diamond has a so large band gap. So that means electrons below the valence band is very difficult. These electrons are very difficult to jump across this huge distance and reach to the other side and become the current. It's likely not possible. So that's why the diamond is very good for the insulating property. So therefore, why the concept of band gap is pretty important, because that can help us to understand the electrical characteristic, especially related to the current. And in between, for these two, silicon carbide, gallium nitride has a band gap which is larger than 3 times larger than silicon. So that means the electrons here still might have a chance to reach in the other side. But of course, the leakage current is already very low because the band gap is larger. So that's why, from the materials point of view, the large band gap, it means we have the very low leakage current. So I think that's the most important concept, that how this material property in the end to influence our characteristic, especially I think in this classroom we are all the engineer that are interested in the semiconductor, so we should pay attention to all the electrical result, for example for the current, for the voltage here, and then the material property of the band gap in the end will influence the current in the semiconductor materials. Okay, so that's the first part related to the materials. And next, we'll start to talk about the junction. So if we look at the junction, actually there are the 4 types of the junction that will be happen in our semiconductor device. The first one is a metal and semiconductor. That means that we will put the metal on top of semiconductor, and in between, there's a junction happen here. And also, the second case is something that we already mentioned, that if we put the P-type of material connected with the N-type of material, and for sure, there could be something happen in this region. And also, it can be possible that we try to put the 2 different materials together. In this case, it should always the same material like all other silicon, but just with a different doping. In this case, it can be the 2 completely different material. So it can be the silicon put on top of the gallium nitride, the compound is put on top of the silicon. That can be possible. So therefore, there's still one junction here. And also, in the case of the metal oxide semiconductor, the interface between here and here, that can be considered as a junction. And therefore, this interface for the different material, for different doping, that can always cause a lot of the different physics inside. So the first one, the metal semiconductor. So the metal semiconductor in general can be considered the 3 different types. The first one is Schottky contact. And second one is the ohmic contact. And third one, which is a metal semiconductor transistor. It's generally called as the MOSFET here. And before we discuss these 3, you also have to be aware of that in the MOSFET, the one that we are most interested in, in this structure, we should also figure out where is the place that can have the metal semiconductor junction. So this is, for example, let's say this is a P-type substrate. And we have the N+. Here we have N+ here. And from the previous introduction, we have known there's a dielectric, there's a gate here. But however, this is something that we don't actually draw before. We know this should be the drain side. That's where we apply the drain bias. This should be the source side. We apply the source bias. But actually, we still need to have the metal electrode. So once we apply the bias, we definitely have to probe on the metal pad here. So that means we also need the metal electrodes in the drain, and then the metal electrode in the source side here. So this is so therefore the metal and the semiconductor junction is shown in here. Right? So this is a place where we have the metal, we have a semiconductor. And this is a place we have a metal, we have a semiconductor. I think it's better just write in this way. So we have the metal, semiconductor, so that's a place where we have the metal semiconductor junction in the MOSFET, this kind of a device architecture. And it's important to know that since these are the two different materials here, so we can expect that the issue has a certain resistance in between. And that's usually we call this as a RC, the contact resistance. So that should characterize as shown as the RC here. This is because the metal and semiconductor, these are the different materials. It definitely has a certain resistance in between here. And therefore, we have to figure out that what can be the contact type in the metal semiconductor. And they are generally related to the first one. It's called the Schottky contact. So the Schottky contact is if we look at for the IV characteristic, this is a current versus a voltage. So the Schottky contact has a characteristic like here. So that means you have to apply up to a certain bias, you start to have the current conducting. But if you apply below the certain bias, you won't have the current conducting here. So this is a typical characteristic for the Schottky contact. And the another case, the complete opposite case, that would be the ohmic contact. So the ohmic contact, it means that if you look at the IV characteristic, current versus the voltage, the ohmic contact has a curve that's always goes through the zero. That means wherever you apply the voltage here, it always has a current generation. You apply here, you have the current here. And then that's also is related to the different contact characteristic. So if we can make the contact has this kind of characteristic, that actually suggests that we have the very low current. We have very low resistance, we have the higher current. Because in this case, your resistance is lower. So in the case when we design the transistor, for sure, we always want to have the lower contact resistance. That means we want to have the better ohmic contact characteristic in this place. The better ohmic contact characteristic can give us a lower contact resistance here. So that's an important part for the first one related to the metal and the semiconductor. And once we talk about the part, there's a dedicated chapter related to metal semiconductor. We will talk more about the physics inside. And this just a brief recap that in the end that how these IV characteristics look like. And the third one is metal semiconductor transistor. We will also talk about this, but that will be the last chapter. The next one will be the bipolar junction transistor. The next one will be the PN junctions here. So we have already seen this case before, and there's several difference related to the PN junction. The first one is a PN diode. And the second one is a bipolar junction transistor. This is a BJT. And the third one is a junction FET. That's what we call the JFET. And the last one is a thyristor. Which is a structure that has a PN-PN combination. So I think for PN diodes, for sure, this is already the structure for the PN diode. And then in between, we have the PN junction here. And for the BJT, that's a part device should show like here. So for example, in the case of the PNP, or in the case of NPN, so we all have the PN junction. So that's for the BJT here. And also the one with a thyristor, which is this is structure which we have the PN here. And also the understanding of all these junction is important to understand the characteristic. And in the case of the JFET, the JFET structure is look like here. So we have the N plus, and first of all, this is a N-type substrate here, and in the JFET, we don't have the oxide here. We actually, in the channel region, we will make this part as a P, and we will apply the VG here. So this is a JFET. So we will control the channel by applying the bias in the P-type region in the channel. And in this case, for sure, we have the PN junction here. This is the place where we have the PN junction, and that will highly determine the characteristic. So now I hope you can understand why the PN junction is super important. So if you look at every semiconductor device book, it's always, once you finish the quantum mechanics, the first part will be start to go through the detail related to metal semiconductor junction and also the PN junction. Because if we understand the metal semiconductor junction and PN junction, the later related to the transistor, no matter for the BJT, for the JFET, or even for the MOSFET, because for MOSFET we also have the PN junction, and this physics can be also applied to the real transistor. Okay, so we will take break for the 10 minutes and we'll come back later. Did you sign up last time? Yeah. Did you come to you sign up my like the sign up sheet? Do you register the sign up sheet?
Yeah, I got your email.
Ah,
Okay.
It's better I sign somewhere because this microphone. Yeah, this is the NYCU. Yeah, for the micro electronics info system. That's for the ICT. Go there, you choose for that.
Another question is about to go to the
Health feature. Yeah, no problem. Yeah.
My question is are we getting the homework today? Are we getting the homework today?
Oh no. I think everything will post in the history. You join the Facebook? You have to check for the last week's slide. And you have to
enter the
issue. You have to enter once you go to E3 and then you look at for the introduction.
Yeah, but I have to give it to them so they can register me.
Yeah. We won't have a homework today. Yes, I received mail, but however, actually we checked the record, we didn't see anything. Yeah, we didn't see it. We don't record for the attendance. Every class you have to sign up for there's some slide that you have to register to prove the yes. Yeah, but that's every class provides the new code.
Actually, I attended all of the same.
Yeah, but that's because everyone did the same. They all pass. Everyone has the record. And also one more thing is that I please say the deadline to reply because the school needs me to submit the score, and once the score is submitted, there's no chance to reply.
But actually, like, I couldn't the results because like it need that we present.
That's not my problem. That's not my problem because yeah, that's why I really mentioned the mail. You have to reply if there's any issue. You have to reply me with a certain deadline. Because once the score submit, I cannot reply, and also we don't have your record for your attendance.
But I believe like maybe you're familiar.
I'm sorry I have to do this because everyone doing the same.
There's gonna be a requirement for you to.
They have to read. You have to enroll another seminar.
I don't mind like okay. The thing is it's good.
I think the seminar has there's no score for the seminar. Yeah, I'm sorry I have to tell you this because there's one thing. First one, everyone is doing the same. No one has a problem. And that means my rule, my assistant didn't have the problem.
Like your chicken fried name every time.
No, I don't choose the name. I provide the
Like you know, like there was like a chicken fried name every time.
Yes. Yes, but that's a randomly check. But you have to also use the QR code to sign up the name. Yeah. And also one more thing, if you let me know before the deadline, probably there's just something we can do. But right now, the system is already broken. That's why I mentioned the mail that if any issue you have to reply me. And you reply me so long, that everything is wrong. I cannot do anything. Okay, so please, yeah, also for this part, you are welcome to be careful. Also by the end of the semester, once you provide the final result, you have to check your mail.
So it's like just like a case I was in Taiwan, so I couldn't really follow up.
I'm sorry about that. But I think the seminar should be fine because that actually doesn't have the score. It's a pretty relaxed class. Yeah. Okay. But I'm sorry I cannot allow for another enrollment because there's already reached the maximum capability. I received mail, and the rule is that you need to come in the first class and sign up, join the sign-up-ship. Yeah. Yeah, I'm sorry about that. Because it's already quite full. Yeah, if every student comes in class want to sign up, I cannot handle so many students.
Yes, I was in New York.
Yeah, I know. I remember you, but I told me. Yeah. No, I'm sorry about that. Okay.哎，这是有题目吗？是吗 ？OK。哎，还没有确定呢，怎么样？看到那个学校的哎，我那个还没有 update，就是那个只是按照去年的，我没有先把那个 update 成那个现在的 schedule， 对，虽然还是有点，然后有什么在什么。只是期中考就是4月份，对，是差那种。对，然后因为我们这学期有分计要去实习，然后4月3号有去报到。OK， 这个因为我们这可能期中考，那你实习要很长。对对对，哎，什么实习怎么只有2个月？其实可是实习的话，可是这样的在上课来。我们有把那个空的那个要上课的天数排，哦，一个礼拜有这个去3天。哦 ，OK， 可是那这样子，我说那这样跟那个期中考有什么关系？对。他刚好那天是全部人都可以到。哦，4月8号，4月8号是礼拜1，对对对，他刚好礼拜1。我可能没办法完全的确认，因为也有可能，或是可能会认为，对，这样看上课名字。因为4月8号刚好是放完假的。对，或者是说，到时候再看，至少我先知道一下。好，谢谢。 Oh yes, yes, I have received it. Yeah.
那其他车会到吗？
Okay. How many? Yes. So you passed all the class last semester, right? Just some of them didn't reach the scholarship, but I think you will get the tuition waiver. Yeah. Okay.
哪里有白纸？白纸。学成主任，那个你签给他。
我有同意。OK。哪个？
再签一张。
哎，还不会，因为我还没 update，还没 update 上。对，所以这个我觉得时间点好像不是一样，是吧？好像是2月10，就3月10号 holiday，对，那是对，还没有 update。对。那下礼拜下礼拜会放假，下礼拜放假，只是说我说这个时间，对日期，日期是对的，OK，然后就这样子，上课的这个时程不一定会，就是里面的这个每周进度不一定会是一样，对，但是没错，3月4号应该是我下个月我出国就会放假，那之后可能会再根据这个上课时候的安排，对，你是有什么的特别的想要确认的吗？期中题目吗？对，期中考我是写4月22。哦 ，OK， 那因为主要是会以上完 PN 章选为主，对，所以到时候会再来上，对，然后期末考应该也会在这个时候，对，哦。这个是跟我讲的。哦，这条关节。 Okay, so the next we will continue for the junction between the two semiconductors. So this is usually we call this as a heterojunction. So there's some example. For example, the LED. And the second will be the laser diode. And the third one is HBT. So the full name is a heterojunction bipolar transistor. And last one is the hand. And the full name for the hand is high electron mobility transistor. So that's we call the hand structure. So one of the examples for the semiconductor, two semiconductors are combined together. For example, if you look at for the gallium nitride hand, the basic structure for the gallium nitride hand is two types of semiconductors that connected on top of each one. For example, is aluminum gallium nitride on top of the gallium nitride, and these are the two different semiconductor material. And for sure that the interface between the aluminum gallium nitride and gallium nitride has created some of the very unique physics property. And in this case, they would be the electrons in this interface. And usually we call this as a two-dimensional electron gas. That's a 2DEG. So that's a very unique properties only happen in the system with aluminum gallium nitride on top of gallium nitride. So this is an example that the junction between the two semiconductor materials that can create a certain unique physics properties. And the gallium nitride hand nowadays is mainly used for the RF and the power application. And the last one is metal oxide semiconductor. So that I think this is directly related to the MOSFET transistor. So in the metal oxide semiconductor, it's often seen in the first one is a MOS capacitor. And the second one is a MOSFET. And right now, I think we can divide the MOSFET. Inside the MOSFET, actually, there are the two small components that highly determine the MOSFET characteristic. The first one is MOS capacitors. The second one is a PN junction. So that means if we understand the MOS capacitors, if you understand the p-n junction. And later on, when we talk about the MOSFET, and that should be not problem for you, because that's a physics property. The electron transport is already mainly dominated, influenced by these two. Okay, so now we finish the introduction for the junction, and then in the future class we will start to discuss each junction case. And before we continue to go to understand the semiconductor device, there are several fundamental theories that can help us to understand the physics inside. The first one is well known. That's what we call the quantum mechanics. So the quantum mechanics is mainly related to the Schrödinger's wave equation and also the Venn diagram series. So we will talk about the quantum mechanics later. And the second one is a carrier transport. Carrier transport. So in here we will discuss the bipolar transport equation that's related to the electrons and holes, and also related to the diffusion, drift, generation, and recombination. And the third one is a Poisson's equation. So the Poisson equation is very important. This is the equation to derive the electrical and potential distribution based on the charge distribution. So later on, we will also introduce all these three fundamental theories. Then we start to introduce the solids, type of solid in the semiconductor. We consider that's related to the solid, and there are the different kind of the solids that you need to understand. That's related to the amorphous, polycrystalline, and single crystal. So amorphous material is have the order with only few atomic and molecular diamonds. So you can see this is a schematic for the amorphous. And polycrystalline is a material has a high degree of the order that's shown in here. And the last one is a single crystal material have the high degree of order and the regular geometry periodicity as shown in here as well. So its electrical properties are better to those of non-single crystal material, since the grain boundary tends to degrade the electrical characteristic. And in here, this is a grain boundary. So this is a grain boundary. So as long as we have a grain boundary, that's always will have the chance to degrade the electrical characteristic. And when we talk about solid, so we will start to understand the crystal plane and how the crystal structure for the each semiconductor material. For sure, in here we mainly use silicon as an example. So the first one is space lattice, and we have to divide the two terms here. One is a unit cell. So unit cell is a small volume of the crystal that can be used to reproduce the entire crystal. And second one is a primitive cell. So this is the smallest unit cell that can be repeated to form the lattice. And in many cases, it's more convenient to use a unit cell, not the primitive cell here. And the relation between this cell and lattice is characterized by the three vectors as shown in here. So if you consider the unit cell as shown in here, which is a cubic, and we can actually characterize this unit cell by consider the vector as here A, B, and C. So we can use the vector of A, B, C to characterize this unit cell, and therefore the R can be represented as shown in here by using these three vectors A, B, C. And the periodic arrangement of the atoms in the crystal is called the lattice, and there are several different arrangements for the lattice. The one shown here is we call as a simple cubic. So in the case of simple cubic, the number of atoms per unit cell is, we have the 8 atoms in the corner. So we have 8, and then each one only contribute for the 1/8 portion. So in the end, the unit cell is equal to 1. So that's a very simple calculation. We have 8 in the corner, and each one only contribute for 1/8. So then result will be, in this case, simple cubic, the unit cell is 1. And the second case is a body central cubic. Sometimes we just call this as a BCC. And here again, how many unit cells in the BCC structure? Which we have 8 still the same in the corner. We have 8 atoms in the corner, and each one only contributes to 1/8. But now we have the additional one in the center, so that means we have to also consider this one. And in the end, we have the 2. So number of atoms per unit is 2. And then the last one is a face central cubic. For face central cubic, still the same. We have the 8 in the corner, and each corner will only contribute to 1/8. But now we have also this in the face, so we have a 6 in the face, and each one is contribute to the 1/2, and therefore the total here is equal to the 4. So the number of atoms in the unit cell is 4. So I think that's a pretty like the straightforward calculation, but at least this gives you a certain basic understanding of how do we calculate unit cell in the certain lattice arrangement. So once we have idea for the how many atoms in the per unit cell, then we can start to calculate the number of the density. So as shown here, if we consider this is a simple cubic, we have a 1 point per cell. So that's already shown in the previous slide. But now if we are interested in number of the density, actually we just over by the volumes here, then we can have the number of the density can be calculated from here. So the similar case can be done for the case with the BCC and an FCC. That's already something we have been shown before. The BCC has a 2 and this has a 4. And if we consider the realistic with the silicon and germanium, and that's actually the diamond cubic structure is obtained with the 2 FCC sublattice. So we have to consider, that's why we have to introduce simple cubic BCC and FCC, because in realistic, like the silicon case, we have the 2 FCC sublattice, and each one will be, these 2 will shift along the body diagonal by 1/4 cubics edges here. So you actually have the 2 FCC, but they have a certain shift along the certain angle, and that's how the silicon structure look like. And since we have started to talk about the crystal, and this is important, like how do we define the crystal plane? And to define the crystal plane, we have to introduce the Miller index. So this is an example that if you try to consider this crystal structure and you want to specifically to tell that we are you refer to this plane, and this plane is called 001, and this plane is called 111, and this plane is called 110, and how this number is coming, and therefore we have to introduce the Miller index. So the Miller index is to describe the lattice direction and planes here. And how do we do to calculate the Miller index here? And there's several procedures. And first one, as shown in here, we are interested in trying to define this plane. And if we look at the intercept in the x, y, z, the intercept in the x coordinate is 3. The intercept in the y coordinate is 2. And intercept in the z coordinate is 1. So the first step, it calculates the intercept in the x, y, and z axis. So that's 3, 2, 1. And now we have to do the reciprocal of the intercepts and multiply by the lowest common denominators here. So what does this mean? This means that first one we do the reciprocal of this number. So that would be the 1/3, 1/2, 1/1. And now we times the lowest common denominator, which will be the 6. And then this will become 2, 3, 6. So that means the plane referred to here is 2, 3, 6. So finally, the plane here has its own unique name, and this is how we calculate from the Miller index here. So we will use this one to refer to the plane shown here. And there's some more rules. For example, if we are interested in the plane that has a negative intercepts, like for example the first case here, so intercept here is 2, 3, but this is -2. So again, we still do the reciprocal. So that would be the 1/2, 1/3, 1/-2. And we multiply by the lowest common denominator, which will be 3, 2, -2. Oh, sorry, 3, 2, -3. But now, in the plane, in the Miller index, there's no negative. So that's, in the end, will become the 3, 2, 3, but we put a head in the number that has a negative value here. So in this case, that's a Miller index to describe the plane has a negative interface. And also, we could be interested in the intercept could be the plane that had the one intercept is approach to the infinity. So if you look at this intercept here, that would be 2, 3, and approach to the infinity here. So again, this is 1/2, 1/3, 1/infinity. And then that will become the 3, 2, 0. And finally, the Miller index is shown here. So as long as there is a 0, that means there's a place there's a certain intercept that actually is approached to the infinity. So here's some more about the Miller index here. So as I say, the negative, that's also put the head in a certain axis if there's a negative intercept. And this represents a family of planes. And this represents a direction. And this represents a family of the directions. So that's some more rule about the Miller index here. And you can see this is, for example, this one. This is a plane for 1, 0, 0. And the directions here. This is direction for the 1, 0, 0. And this is a plane for 1, 1, 0. This is a plane. So in general, it's a very simple calculation, but that's already quite useful. Especially later on, we will provide some examples. This is very old knowledge. This is just the first chapter of the semiconductor physics. But this information that's already is useful for you, even for your own research. Later on, we will show certain example. And when we consider bonding, this is just a quick general, like the introduction. They can be the several different bonding. The first one, it can be the ionic bonding, covalent, metallic, and van der Waals. So consider for the ionic bonding, it's a type of chemical bond that involves for the electrostatic attraction between the certain or charged ions. In a crystal, negative charged ions tend to be surrounded by the positive charged ions, and positively charged ions tend to be surrounded by the negatively charged ions. I think this description that's easy to be understood. You can go through by yourself. And the next one is a covalent bond. So covalent bond is result in the electrons being shared by these two atoms here. So the covalent bond is a certain. That's more important for us. So here is a case. We all know there are the 4 electrons in the outer shell of the silicon. If you go back to the high school chemistry or general chemistry when you study in the college, you should still remember there's a certain concept to describe some of the outer shell electrons here. But it's just short summary. In the silicon, you have the 4 outer electrons. 4 electrons in the outer shells. So therefore, if you consider the silicon and silicon bonding, it's actually the 4, these, each one will be contribute to 1 and share. And therefore, that's form the covalent bonds here. So the silicon itself has, for example, this silicon itself has a 1, 2, 3, 4. And another one is come from the neighboring silicon, and that can be formed for the covalent bonds. And there's something more like the metallic bond or van der Waals bond. You can look up by yourself. So when we consider the solids here, there's a certain things we have to understand. It's not everything is in the perfect. There's always some of the imperfections and some of the impurities in the solids here. So the imperfection, like the first one, is they can have the vacancy. So this is a typical two-dimensional single crystal lattice, and ideally they should have all certain atoms in each place, but unfortunately there could be some problem that some of the atom is missing, and in this case we can have the vacancy here. Vacancy is in Mandarin we call the 空缺, but the vacancy not can be only used in the semiconductor. The vacancy is a very general words that we can use in our life. For example, when you try to apply the job, you have to check, say that do you have the job vacancy, do you have the position vacancy. That means that 你有没有职位上空缺. So that's also can be used in the daily life, especially for the job apply is often used as the job vacancy. And also in our like the daily life in the bus or some of the train, you will always look for the vacancy of the seats. So in general, the vacancy should not consider this is a very technical term, but actually it's a term that use our daily life. It just represents there's an empty place, so that's a vacancy. So in real crystal, an atom might be missing from the particular lattice side here, so that's the vacancy. And on the other hand, it could have what we call the interstitial. So interstitial is this is a general like the lattice plane, but unfortunately it come out is something that come from somewhere, some other place, and this is occupied in the place that it should not have the lattice. So that's we call this as an interstitial here. So this is also we consider as imperfection. In the end, that becomes a problem for us here. And also, it can have what we call the line defect. So line defect is that if you consider this is this is very often happen in the semiconductor and semiconductor, because these are the two different materials. So for example, this can be the one semiconductor, this can be another semiconductor, and it always goes a problem once these two want to be connected with each other. Let's say in the practical case, we might interested in the bottom use a silicon, but on top we use another compound, for example like the gallium nitride. And in realistic, you will often find out that there's a certain missing here, and that's we call this as a line defect. And how this actually will influence for our characteristic. If you imagine the crystal structure is shown in here. And if we have the here, atom here, atom here. So the vacancy, this is a place where there's a certain missing atom. So that's for the vacancy. So the vacancy means that it's a empty place, just like in the bus, in the train, or in the company. If there's a vacancy, that means that somebody can try to come and sit there. So if we have a vacancy in our semiconductor material, the problem is that it can have some additional carrier come from outside, who might just come here and sitting in this place and become the negatively charged. For example, this is case of the electron here. And that creates the issues what we usually call as the trapping issues. And moreover, the problem is that the electron, once they come sit here, they probably won't sit forever. They probably will sit for 1 minute, 10 minutes, 1 year, 2 years. In the end, this electron might gain some additional energy, will also run away. And that's what we usually call this as a detrapping. So now the problem is that this system is become unstable, because sometimes you have somebody come, sometimes this someone will leave, and you wait for another while, somebody's come, and then after a moment this will leave. Imagine if you are working with 5 people in a group, and the team member is always come and leave, and your system, your team is become very unstable. That's also the same for the semiconductor. So this is become the instability. And instability, it actually is the same meaning of the reliability. So that's become the reliability problem. And the reliability is something difficult to avoid, because it's very difficult to guarantee that every place is perfect. It always has some imperfection in the semiconductor material. But in the end, that will become reliability of our electronic device. So what should we do is we have to understand this instability, and in the end try to figure out certain of the solution. So that's a kind of the correlation of the material science in the end to our electrical result, or certain like the product quality. And here's something more, just for your reference, that of course, if you go inside, try to understand this, is very complicated, but here just quick go through that there's a certain impurities in solids as well. Impurity may be located in the normal lattice side, in which case they often be called as a substitutional. So that's a substitutional. And also there's an interstitial. So that means interstitial is that this is in the place that between the lattice. And this is just the schematic for your reference. Okay. So in the first introduction, in this class, just overview for the materials and crystal and also Miller index, and that's a very basic part. We haven't go very detailed for semiconductor device, but I believe the knowledge we learn from this class, that's already can help you to understand the certain very advanced study for the literature. So this is an example I want to show. Also in this class that we will share time to time, we will share some of the publication in the journal, in the academic, and try to help you, teach you how to understand the academic writing. In the end, you will know how to do the academic writing for the later, because I think most of you here are the graduate students, so academic writing is very important. But to be honest, academic writing is not that complicated as you expected, because when you try to write the academic paper Actually, we prefer to write in the very simple, straightforward way because we are not writing as a novel. So we don't have to build up very complicated story. Our goal is just want to make sure our reader can understand in the very efficient way. So here is an example I want to show. The paper title is Performance Dependence of a CMOS. So this term is already mentioned in the last class. So that means with 2 classes already, finally probably you can start to have a sense of the certain keywords in the semiconductor. And on the silicon substrate orientation of the ultra-thin oxide nitride hafnium oxide gate dielectrics here. So if you don't understand the oxide nitride hafnium oxide, that's fine. But in here, with the knowledge of the 2 classes, I think it's roughly you can get a sense that what this paper will be talking about. So in somehow the paper just talk about there's a device called CMOS, and we try to understand that there's a silicon substrate orientation for the certain dielectric. These all are the terms we have been mentioned. And what is orientation? Orientation is actually shown here. 100, 111, 110. What is this? Actually, this is just a Miller index, right? You probably, in the beginning, you will feel like, okay, why do I have learned the Miller index? And that's looks very simple, probably it's not very useful, and the calculation is also very simple, it's very straightforward. But as you can see here, that's still very important. That's why we introduce the Miller index, because in the certain research, in certain understanding, we do use this one to refer to the plane we are interested in. So you can see, when we talk about the crystal orientation, here is a Miller index is coming. That's why we have to understand what is Miller index here. There's a whole mobility, blah, blah, blah. And then again, in the 110 service. So that's why, again, to illustrate that we need a certain name to indicate the plane we are interested in. In here, he mentioned for 110 service. So that's a certain plane in the crystal. And compare with 100. And CMOS driving current is nearly symmetric on 110 orientation and 110 substrate. So in general, this is just a paper to discuss about the plane in your material with a different plane that shows a different electrical result, and certainly is related to the performance. The performance here is mainly considered for the current. It's related to the current. Okay, so now we can try to see one by one to see that how actually the academic literature organized in this way. This paper, you can see these are the all Western people, so the English writing should be very native, so should not have any grammar or structure issues. So it's good for us to learn how to write the paper here. And first of all, you can see that the title is a Performance Dependency of CMOS silicon substrate orientation for ultra-thin oxide nitride hafnium oxide gate dielectric. And you can find out that actually the first sentence in the abstract, dependency of a CMOS performance on silicon crystal orientation has been investigated with equilibrium gate dielectric thickening less than 3 nanometer. So you can find out that the first sentence here is exactly just a refresh of your title. So that means if once you can write the title, it should be also very easy for you to write the first sentence of the abstract, because that's just purely reflects the meaning. What they want to say is exactly the same. Of course, the keywords also the same. CMOS, orientation. Here is orientation and dielectric. Of course, there's some additional detail, but actually, if we remove all the detail, I think the meaning won't change. The meaning are exactly the same. And later, you can see that in the abstract, usually we will try to identify in the most of the literature, the academic paper writing, we try to identify the three main contributions for this work. That will become your three conclusions. So the first conclusion is shown me here. The whole mobility enhancement of the more than 160% has been observed for both oxide nitride, hafnium oxide dielectric on the 110 surface compared to 11100. So that's the first conclusion. And second one, CMOS driving current is nearly symmetric of a certain orientation, but without any degradation of the substrate slope. And also the third conclusion, and around 68% of the enhancement of the driving current has been seen on a certain substrate with a certain blah 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 detail. But anyhow, you can see this just a 1, 2, 3 conclusion. So when we try to write the academic paper, it's also the same. First, we define the title, and first try to figure out that what would be the three major contributions for your work, and we just try to write the 1 to 2 sentence, try to describe each conclusion in here. This is 1, 2, 3. And then the interesting thing is, if you look at the summary of this paper, it's the same. The first sentence are another rephrase of your first sentence of the abstract. So the first sentence, electron hole mobility has been measured in the CMOS device on silicon substrate with a various crystal orientation. So you can see the meaning of this sentence are the same meaning of the first abstract. They are all the same, like the title. So when we try to write the academic paper, actually what we are doing is just try to again to remind the reader that what's actually our main point of this study. We don't need very complicated like writing. We don't have to write in the very hiding way. What we actually want to do is just to go very straightforward, to use a simple sentence and to very opening to let the readers to understand. In Mandarin, we have actually when we learn the Mandarin article writing, there's a method called the 开门见山. So that's exactly how we write the academic paper here. So again, the first conclusion will be also summarized in here. The second conclusion here. The third conclusion will be here. So the summary is just also another rephrase of the abstract, and it's still a sense to illustrate again there are the three conclusions and what's the conclusion detail. So if you start to write the academic paper, actually you define the title, you finish the abstract. Abstract is very similar to the conclusion. Then that's almost like the 30–40% of the work has been done. And in the middle part, just lots of the data, results, discussion to prove your conclusion. That's all. So if right now, if you try to, when you do the research, you will do the survey to try to look at the literature, whether are the useful for you or not, because you won't read every paper in detail. For myself, I actually didn't read in every paper in detail every time. I only look at the one I found out that's really useful for me. So in this case, you just need to quickly read the abstract, quickly read the conclusion, summary, and you can figure out that whether this paper will be useful for you or not. So far, if you look at this paper, we don't look at any figure, we don't look at any discussion. We can already understand what's their purpose. So the purpose of this paper is described that he tried to fabricate a CMOS. So CMOS is considered as NMOS plus PMOS in the substrate with a different orientation. And he found out that there's a certain orientation can improve the performance. And there's a certain orientation, there's a certain performance degradation. That's all. Even we didn't start to look at all the measurement result yet. We already have a clearly understanding what's the important message come from this literature. Of course, we will still quickly go through some of the key figures. You can see that with the knowledge of the Miller index, you can already understand this, the 110, and with a different way to describe. That's already something mentioned in the previous slide. Here. So that's already, this is the the y-axis related to the whole mobility. This is electron mobility. Again, this is just a lot of the Miller index here. That's just refer to the different orientation, different crystal plane. Okay, so probably you know, if you are the fresh student, you should start to get used to use Google Scholar. If you're a graduate student, you are a little bit senior student, that should not be, you should be already familiar with. So usually we will all use Google Scholar to look up for the literature that interesting for us. So just please do not use regular Google. Please use Google Scholar, because that can give you more efficient way try to find out the literature that you are interested in. Okay, so here is the last part of the slide, and then we will end up the class today. And also one more thing, want to remind that there will be no class on the next week, because I will have to go abroad for joining the certain conference. So we will find some time to make our class in the future. And also one more last thing, want to remind, because still have some new face today. If you don't join the class in the last week, you have to look at the recording video last time. But here I just want to make the reminder for this one. That's important, because I only post the lecture notes in the Facebook, because I actually didn't really get used to the system in the E3, because the E3 is changed over time to time, and always sometimes it will crash. So I will try to not use the E3 very often. So we only post the lecture video in this group, and also the lecture note, and also the lots of important announcements. So you have to join this one. If you already apply and I didn't approve it, you just let me know. That's the first things you have to know. And second one is that some of the new face here, I'm not sure that everyone is already know. Now we start class from 9:30. That's for the convenience for you and for me, for everyone. Okay, so we will end up the class today. If you have any question, just let me know. So we will see each other 2 weeks later. Thank you.